We are going to be taking a look at a very basic introduction to logarithmic functions. Now, before we get into those, we're going to look at where logarithms come into play. And every operation that we have has its inverse. It has something that will undo it. So addition has subtraction, multiplication has division, and nth power has an nth root. So what about exponentials? When our variable is in the exponent, we need to have something that will undo that. It needs to have an inverse. Well, that's where logarithms come into play. So exponentials have logarithms as their inverse, and logarithms has exponentials as their inverse. Okay, well, you might be thinking that some of them are so easy we don't need to have this special crazy name, because if we have something like 2 raised to the x is equal to 4, you can pretty easily figure it out that x has to be 2, because 2 squared is 4. If you had 2 raised to the x is equal to 8, pretty easy to figure out that x has to be 3 because 2 raised to the third is 8. And 2x to the 16th, x would have to be 4 because 2 to the 4th is 16. Those aren't the ones that cause the problems because you can figure them out just by intuition. But what about if you had 2x to the 6th? Now, it would have to fall somewhere in here. It has to fall between 4 and 8, so our answer is somewhere between 2 and 3. But actually finding that exact answer is where the challenge comes in. And that is where logarithms come to our rescue. They will allow us to figure out what that exponent of x would have to be. We aren't going to be doing that in this video, actually figuring out how to find that value of x. We're just going to look mostly at how logarithms and exponentials are related to each other. So just like if we had x plus 5 is equal to 20, we would use the inverse, so we would minus 5 from both sides in order to solve for x. That is what we would do in this situation. We would do a logarithm in order to figure out what our value of x is, because a logarithm is the inverse of an exponential. Okay, so how are logs and exponents related? Well, if I had 2 raised to the x is equal to 4, first thing we need to look at is 2 is what we call our base, and x is what we call our exponent. And then 4 is generally what we would call our answer. Well, with logarithms, we rearrange it. And anytime we're doing logarithms, we usually refer to them as logs, just for short. So we would say log base 2. Notice how the base here has dropped down and has become a small, but it's still called the base. So this would be log base 2 4 is equal to x. So our answer has now come on this side of the equation, and the exponent, that thing that we're trying to solve for, is now our answer because that's what we are trying to find. We're trying to find that exponent. So now we would read this expression log base 2 of 4 is equal to x. And this is how we rearrange exponentials to logarithms, and vice versa. So if we had 17 to the x is equal to 200, we would rearrange it. The 17 is our base, so that's going to be the small number down here. The 200 is going to come over and we're equaling x. So log base 17, 200 is now equal to our x. When you have a logarithm, the value over here is the exponent. Okay, we can do it without numbers. We can do it with a different type of visual representation just to see the setup. So if I had square raised to the circle is equal to a triangle, the square is going to drop down here because that's my base. The triangle comes over, and the exponent is what I'm equaling, so the circle. So it would be log base square of triangle is equal to the circle. So that's kind of how the rearrangement of them goes. It does take quite a bit of working with them to become fluent in rearranging them. You're probably going to have to practice rearranging them quite often. So, what does a log do? It allows us to solve for that unknown exponent. So now if we were asked to evaluate log base 3 of 81, the first thing you would want to do for now is rewrite it as an exponent so you can get a more comfortable feeling of what it's asking. So here is our base, and I'm going to set it equal to x because it's equal to some unknown power. Well, remember, this is our exponent over here. So we have to take our base, which is 3, raise it to our exponent, and that's going to equal 81 for us. So then you have to ask yourself, well, 3 raised to what power would give me 81? Since this one turns out to be like a nice whole regular number, you can find out that x is equal to 4. We will do ones that don't turn out to be nice whole perfect numbers later. Okay, now this next one, we're going to set up the same type of way. So I'm going to set it equal to x, and I'm going to first write it as an exponent. So I'm going to take my base of 1/2. 1/2 raised to what power is equal to 8? Okay, this one is not nearly as obvious as what the last one was. Now, one thing you might be looking at, well, to get 2 to turn into an 8, I know it has to be to the 3rd power. But if I do 1/2 to the 3rd, that's going to give me 1/8. That's not going to give me 8. Then I have to start thinking about, well, how can I change 1/8 into 8? Well, if I were to do the reciprocal of it, so if I were to flip the bottom to the top and the top to the bottom, it would give me an 8. So you want to think about your rules of exponents. What rules of exponents mean that you have to cross the line and switch the sign? Okay, that's your negative exponent. So this is telling me that the 3 is going to get me to the number 8, but it's going to be in the wrong spot, so I'm going to have to make it be a negative 3. Because if I did 1/2 to the negative 3, that would be 1 to the negative 3 over 2 to the negative 3. Well, with negative exponents, I have to cross the line, switch the sign, so I would have 2 to the positive 3rd over 1 to the 3rd, which gives me 8 over 1. So the answer for this one, x, would actually be equal to negative 3. So sometimes they are a little tricky, and you're going to have to practice looking for those patterns. So the first thing I did was I asked myself, how does 2 turn into an 8? And that was by a 3, and then I had to think about, well, how do I get them to flip? Well, I use negative exponents for that. So it ends up being a negative 3. Okay, now these are some interesting properties that will become very, very important when we do graphing. The first thing, log base b of b is equal to what? Well, if we set that up as an exponential, my base raised to some unknown exponent has to be equal to this right here. Well, notice that these two are the same. It's b and b. So you have to ask yourself, if I take a number and raise it to an exponent, what's the only thing that this exponent could be to give me that number back? So if I said 8 to the x was equal to 8, what could x be? Well, it has to be 1. If I did 27 to the x equals 27, it has to be 1. So this property right here, the log base b of b, when these two are identical, it has to be equal to 1. Has to be. Okay, the next one, a little bit different. So I've got my base of b raised to some unknown exponent, and that's going to have to equal this 1. Well, now you've got to think back to your properties of your exponents. B raised to what power is equal to 1? So if I had 5 raised to the x is equal to 1, you have to ask yourself, what power of x would give me a 1? And that's the 0. So this one, x has to be equal to 0. If I had 200 raised to the x is equal to 1, has to be 0. So this property here, log base b of 1, is equal to 0. Both of these properties are going to be very important when we start doing graphing. Okay, now when we look at logs and we look at your calculator, you should be able to find a button that has that word on it. It says log, and that stands for logarithm. But what you have to understand is your calculator your calculator is set to operate in one particular base of logs, and that is base 10. So if you have just a regular scientific calculator and you see the log button, it is defaulted to be log base 10. There should also be a button on there for ln. And it might be the second function of your log button, or it might be right next to your log button. Well, ln, we call that the natural log. And when you use ln, that's just another way of writing log base of e. So ln is a log that has a base of e, and the log button on your calculator, or if you just see the plain phrase log and maybe it has 100 here, that's assumed to be base 10. If it is a base other than 10, it will have that indicated. So it might say log base 2. If it's a natural log, that's automatically implying that it's a base e. So here's our first set of practice problems. Go ahead and pause the video and see what you come up with for these answers. Okay, the first one, just wanted you to rewrite it. So I had my base raised to my exponent, so 30 raised to the t equals 17. And then the second one, evaluate without a calculator. So this one just said log of 1,000. Well, since there was no base indicated, we have to assume it's a 10. So we have our base of 10 raised to the n. So 10 raised to the n is equal to 1,000. Well, 10 to the third will give me 1,000. And then third one, write it in exponential form. So I take my base of 4 raised to the r. So 4 raised to the r equals 15. And then the last one, write the log in exponential form. Since it's a natural log, that means it has a base e. So this would be like log base e. I have e to the y is equal to my 15. And second set of practice problems. See if you can do each one of these. So pause the video. Okay, these were probably a little bit trickier, but it's still the same setup. So I take my base, so I have log base 7 of 200 equals my exponent. Well, my exponent this time is 4t. Okay, this one, I have a base of 15, so I have log base 15 of j is equal to, well, this time my exponent is a log of 2. So log of base 15 of j is equal to log 2. And the last one, since it's an e, I use natural log, so natural log of 70 equals my exponent of 8x.